So we're in your chemistry in 15, section 2. And we've been talking about acids, bases. And in this section, we're going to talk about whether acid is a strong acid or a strong base or a weak base or a weak acid. So they differ in their strength, and the strength determines how they ionize in the solution. A strong acid ionizes completely to form hydroxide, this hydroxide ion. So a strong acid, just think of a strong acid just getting completely done, and a conjugate base. So usually a strong acid will go with a conjugate base that is a weaker base, but a strong acid ionizes essentially to completely form this, whenever you see this with this positive, you always know it's an acid, and a conjugate base in the aqueous solution. So remember those conjugate, you always have an acid that's forming into a base, right? The common examples you should know and memorize include these very strong acids. So how do we know it's a strong acid? Well, basically we have to look at a table or memorize and know. So here we have, you're going to have sulfuric acid here. Sulfuric acid is a very strong acid. You have the nitric acid here, and you have the hydrogen chloride with the acid here, hydrochloride. So hydrochloride here, and the hydroanalytes with hydrochloric acid, hydrobromide, they combine here. These combining with these are always going to be strong. Since the reaction between a strong acid and water is essentially complete, only a single arrow is used in the equation. So this is just what they're saying, that you have equation here, you only have just one single. That means it's all going to get all the way. This acid here is going to combine with this base, which is considered water at this base, water acting like a base, and it's going to be strong because it's going to go to completion, and it's not going to come back. It's going to go to completion and not come back. So those are very strong. When you have something like this, it's very strong acid. So here's some strong acid and bases. You can look back at this, and see, and you'll see basically, going on to combination with bromine, iodine, chlorine, all of these here with hydrogen producing that hydrochloric acid, hydrobromic acid, hydroiodine acid. Remember, we learned how to enable them, and all these are strong. We have the sulfate, sulfuric acid here, and these here onto. These are strong bases. These have hydrogen in the beginning, considered acids, and these have a metal in the beginning, and they have OH, base. OH means they're a base. Just know, if you look right away, OH, that's a base. Hydrogen, that's acid. So sodium hydroxide here, we know is a strong base. Potassium hydroxide, lithium hydroxide, all these metals with a base of strong bases. Calcium hydroxide, barium hydroxide, all of these, considered strong bases. Okay, strong acids. So you'll just look back at this table, but just kind of knowing here which the strong ones are, and they'll just go to completion. It says, on the other hand, weak acids ionize only partially. So, and most of the acid molecules are present in solution in their molecular form, and very little conjugate base forms. So here we have weak acids. Here is a weak acid, acidic, going on to the base. So you have here. So you have the double arrows, meaning some of it is going through and some of it's not. So it's a weak, whenever you have the double arrows, meaning it's equalizing out, but it's not going to completion. So we have a weak acid going in to that point. So we have the acid and the conjugate base, and the base and the conjugate acid here, but it's forming these conjugates as, and they're not going to completion. Just think, strong means to complete. If you're really strong, you're going to complete the job. And the weak doesn't complete the job. So a lot of times, remember, we know hydrogen is, you have two here, so it's diprotic, they call it. So anything that has 2 hydrogens or 3 hydrogens, triprotec, it's hard to get them to go to completion because they have all those hydrogens. So they could be considered a weak, right? So the first ionization, the first time it goes through, it's going to be considered strong because they're getting rid of the first. And then the second one, basically, let me read this to you. It says, since hydraulic or sulfuric acid there is diprotic, it may lose 2 protons when ionized in water. Only the loss of the first proton is complete. So the complete ionization of sulfuric acid, when you think of hydrosulfuric acid there, does not occur, and this is a strong acid only in its first ionization. So here we have, let's look at this. So here we have this equation here with sulfuric acid here going on to with hydrogen. This is the first going into the second. So just remember, it's going to be harder to lose 2 hydrogens or 3 hydrogens. So the first one it loses is going to be very strong. The second one is going to be a lot weaker, and the third is going to be even weaker. Okay. As for an acid, these are our acids with the H in front. It's always an acid. Similarly, strong bases are bases that completely dissociate into hydroxide ions in an aqueous solution. They are generally hydroxides of groups 1 and 2, which are what? 1 and 2. Remember, those are those metals and alkali metals. And so elements 1 and 2, like sodium and potassium, are most common in the laboratory. So these are considered strong bases. OH means it's a base, right? And so all of these, so if you have all in this column here, so if you have sodium and potassium, and this column and this column are going to be very strong bases, and that they're going to go to completion, meaning going to completion. And so those will be strong bases. So the most familiar weak base is what? Let's see, is ammonia. So that's good to memorize. Ammonia is a weak base, which reacts with water to only a small extent, and it produces ammonium and hydroxide ions. Here's it up here. Here's ammonium, NH3, and when you think of N, you always think of ammonia. So here's ammonium and water, and reacting and at that point to produce hydroxide ions is a very weak. It's losing one, but it's considered weak. So it says you should memorize those and know which ones are which, but it says importantly, the terms strong and weak refer to the extent of ionization of an acid or base, not to its concentration. So you can have concentration means how concentrated the acid is, and so it doesn't depend on its concentration. So it says, for example, 0.1 mole solution of hydronitrite, is diluted. Here we go. HNO3 is diluted into strong acid, whereas 10 moles of HC2H3 hydroacetic acid is not strong. It's a weak acid. So basically you can't go by the mole to find out. So if you have a question, they say, okay, this one is going to be stronger than 10 moles is going to be stronger than 1 mole. No, you can't go by that. That's just a test question, right? So here we have the ionization of strong and weak acids. So this is a strong acid, which is hydrochloric acid. It's always strong. It's in your stomach, very strong before ionization, and then at the equilibrium, it goes to completion. All of it's gone. It all changes to the hydronium, which is the acid indicator, which is H3O ion, and it ionizes the whole thing, very strong. And so here's a weak acid. See how the weak acid it changes, but very weakly. It doesn't produce very much of them. It doesn't produce very much of the hydronium ion, which is acid here. So see, it's just only partial. So this is a weak acid. See the difference between the strong and the weak. That's what this section's about. So here's a picture here, and this table is important. I don't know how you can memorize this, but you know, it tells which acids are strong acids and weak acids and strong bases. See how the strong acids become stronger and weak down here. Just remember, ammonia is a very weak acid. So, and here we have the opposite. We have the increase in strength. This are weak bases and the strong bases down here. So, and reacting, how they react with each other. So, you know, you can look on this and find out, oh, this one looks pretty strong. Acetic acid, here's acetic acid, looks like it's about medium. Nitric acid, right here, looks like it's very, you know, nitric acid looks very strong. Sulfuric acid, so on here you can tell if they're hot. And down here you have very strong hydride, you know, these down here, sulfide, cyanide, all very strong. Ammonia is strong. See the difference between ammonia is a stronger base when it's used as a base than ammonia is a very weak acid. So, and we go on here, up here. Water being right, probably close, you know, to the middle here, in the midst of being a base. Water can act as a base or an acid. So remember, relative strengths, the Bronsted-Lowry acid loses a proton to become its conjugate base, which can accept a proton, and Bronsted-Lowry base accepts a proton. So we're talking about the protons in the midst of the strength, especially with Bronsted-Lowry. So we're going through all this. Just remember this: the stronger the acid, the weaker its base conjugate would be. So if you have a strong acid that's turning, you know, to a base conjugate, and that the weaker the base is going to be, the stronger the base, the weaker its conjugate acid is going to be. So when you have a strong acid, you're going to have a weak conjugate base. That's in the equation. When you have a strong base, you're going to have a weak conjugate acid in your equation. So let's see. Just remember the Bronsted, this protein transfer would be complete in a strong one. So the protein transfer would be complete if it's strong and not complete if it's not. So in summary, let's go. In summary, proton transfer reactions favor the formation of weaker base and a weaker acid. So when you have a proton transfer, you know, they want to favor the formation of the weaker base and weaker acid. So, and this is how it's illustrated here. So you have a stronger acid reacting with the stronger base, and they're going to be in favor of producing weaker. And you can see this weaker see how weak it's coming back? It's strong going, and then the weak, just a little bit's coming back. So it looks like this. It basically is not going to go quite to completion, but you're going to have strong acids and going very strong and coming back weaker bit. When it's coming back, basically you're going to have weaker acids. And here's a strong, here's going to be a weaker acid and a weaker base. And so they're going to see how the arrow is weak. And so, but they're going to come back as a stronger acid and stronger base. So just think weaker to stronger and stronger to weaker, you know. Table, what's it say? Table 5. Let's look back at that table. Oh, we looked at that table already. They're talking about this table here. And my battery's getting low here too, so we better get done with this quickly. Talking about this table as to find out which are weaker and stronger. Note that the strongest acid listed has the weakest conjugate base, and that the weakest acid had the strongest conjugate base. Let's look at those conjugate bases on that table. So this is a relative strength. This is the strong acid will go with a weak base, and a strong base towards the bottom. The strong base would go with a weak conjugate acid. You see, strong base goes with a weak acid, and a strong acid will go with a weak base. Okay, let's look at this example here. Tell the direction of the equilibrium for each of the following. So you have to find out if this is strong or this is strong. You find out on that, and to look back and see if it's strong. If you look back on here, you'll see this is acid, very strong acid. Sulfuric acid here is very strong. And this here, as we're going in here, this would be basically, this is the base, but we're looking at this going as it's sulfur turning into sulfuric. See how it's going to completion here? So we have a strong acid turning into a weaker base in the midst of this. And it's going to be going all the way to completion. So equilibrium then would be towards the right. So here it's explaining. So in this equation, sulfuric acid is the acid, and the sulfate is its conjugate base. So right here, here's the acid. Here's SO4 and SO4 here, so you can see that. And CN is the base right here, and its conjugate is going to be here. So you have two different things going on with their conjugates. One's going this way and one's going this way, so and then we look at this, the HSO4 here is stronger from that table than HCN right here. That's as for the base is and that CN is a stronger base. This is a stronger base, and this is going to be weaker. So the stronger acid and the stronger acid, the weaker its conjugate base. So the equilibrium is going to lie, it's going to always go to the weaker side. So it's going to be strong going in, but weak coming back. So it shifts to that other side. Remember the shift there that we had before. So number 2 here, B. Let's look at this. So we look and we have the phosphoric acid is the base and its conjugate acid. And so we look at the ammonium acid, and ammonia is the conjugate base. And from this table we see that NH3 is a stronger base, and that phosphate then the phosphate, and the phosphate is a stronger acid. So now we can see, let's look how it looks. We're going to just label them. So we're going to see the weaker base, weaker acid, stronger acid, and stronger base. So we're going weaker. This is all going to be weaker as we go here. You can see this H2PO4 ion, and this is the ion. So we're going backwards from the ions to combining the ions. And so we see how it's going the weaker to weaker and onto. So basically the weaker is going this way is very weak, but coming back is going to be really strong, going into the stronger. So you're always going to have stronger to weaker, So the equilibrium is going to lie to the left. Basically, the stronger is going to be coming back. So, okay, that's about it for this section.